We're now going to discuss internal forces. Up to this point in the course, we have discussed external forces. That is, forces that are acting on members. Many times, however, it's helpful to determine forces inside of members. A good example of that would be analyzing a beam or a bridge to determine if it can support the load that is given to it. For this procedure, you must use the designer's sign convention. All reactions in that sign convention must be assumed in their positive senses in order for this to work out. The first reaction is the axial force, which is symbolized with a capital P. A positive axial force tends to stretch this section. A negative axial force tends to compress this section. And you'll notice that I'm showing here a sectioned beam. You would analyze only one half of the section. So, for example, if we were analyzing the left half of the beam, we would draw this picture and the positive axial force would come out of the end of the beam going towards the right. If we were analyzing the right side of the beam, the axial force would go towards the left. We also have a shear force. The shear force is symbolized with a capital V. A positive shear force, if we hold the beam at this side, the positive shear force produces clockwise rotation around the opposite end. Likewise, if we were to analyze the right of the beam, the positive shear force would produce clockwise rotation around that side. Negative shear force then produces counterclockwise rotation around the opposite side. Please remember, we are always assuming the positive senses on these. And the last one is your bending moment. A positive bending moment tends to compress the top of the beam. If we imagine the beam being made out of fibers, the positive bending moment would compress those fibers at the top. So if we're analyzing the left side, the positive bending moment would be going counterclockwise. If we analyze the right side, the positive bending moment would be going clockwise. When dealing with internal forces, then, the procedure is as follows. First, draw a free body diagram of the entire beam. Next, you will find support reactions. It's important to note that we're going to keep all their forces and the distributed loads in their exact locations. Don't try to slide or move them around. Then we'll sketch a cutting plane passing through the location in question, very similar to the cutting planes we sketched when we were dealing with method of sections. And then draw a free body diagram of the desired section. You could draw a free body diagram of the left of the beam, the right of the beam, or even of the center, a center portion of the beam. After that, you'll apply static equilibrium to moments around the point, that is the point where you cut the beam, where it's sectioned. You'll apply static equilibrium to X and Y directions to find the normal and shear forces. Remember your sign convention. When you draw the free body diagram for the section of the beam, you have to use the designer's sign convention. Your standard sign convention, what I'll call your global sign convention that determines positive X, positive Y, and a positive moment, that doesn't change. What does change is the way you assume your reactions. You have to start off with all three reactions in their positive senses. When you report your answers, then you will report either positive or negative. Don't try to use a vector sign. Don't say tension or compression. Report positive or negative. As a final note here, when you're sectioning a beam, make sure to section any distributed loads acting on it. It is imperative that you do so, and I'll show you that in the example here. Here we have a beam with a triangular distributed load acting on the top. The height of the triangular distributed load is 4 kilonewtons per meter on the left end and 0 kilonewtons per meter on the right end. The whole beam is 6 meters long, and it's supported at A by a hinge and B by a roller. We are asked to find the internal forces at point C, which is right in the middle of the beam. Remember, the internal forces, there are three reactions: the axial force, the shear force, and the moment. So here's the beam. I've redrawn it and replaced the roller with a single force perpendicular to the surface, which in this case is By. I've replaced the hinge with two forces, an X and a Y, AX and AY. You'll also notice that I've begun the process of replacing the distributed load with a single point force. When you are finding support reactions, you will want to do that. In the rest of the problem, we are not going to do that. Our distributed load was initially triangular in shape. Remember, the value of the force that replaces the distributed load is equivalent to its area. So I will calculate that in an aux comp. So here I've calculated the value for the force, which is 12 kilonewtons, and it's the location, which the force is located at the centroid of the distributed load. Remember that this equation here for the area and this equation for the centroid are going to vary. The equations will be different based on what the shape is. In this case, the shape is a triangle, so I'm using the equation for the area of a triangle and the centroid of a triangle. So now I'm going to solve for support reactions. You do not have to solve for all the support reactions in the problem. The thing you probably want to ask yourself is which side is easier to analyze. So let's take a look at this beam and figure out what we'd like to do. We're going to section the beam here at point C. And so we'll either use the right side or the left side. We don't have to use both. If we use the left side in the second half of the problem, we'll get this shape over here. This shape is a triangle on top of a rectangle. If we use the right side of the beam, we get this shape, which is just a triangle. The right side is geometrically simpler, so I'm going to use the right side to solve this problem. I'll draw a free body diagram of the right half of this beam. That doesn't affect what I do now. Right now I'm looking for support reactions and I'm going to use the entirety of the beam. But I'm going to solve for the right-hand side of this beam because that shape will be simpler to analyze. In order to solve for by independently, I'm going to sum moments at A. That'll cancel out ax and ay and leave with by as the only unknown. L is going to produce negative rotation around point A, and its perpendicular distance is C. by is going to produce positive rotation around point A, and its perpendicular distance is A plus B. Solving this equation for by yields this. Now we can plug the numbers in, and we'll find by equals 4 kilonewtons. We assumed correctly. Before you continue with the rest of the problem, it's required that you state the equation for the distributed load. In this case, the distributed load is a straight line with a slope. So the function is going to be in y equals mx plus b format. Now, dl is the equation for my line. My 0, 0 is right here. In all of these beam problems, your 0, 0, the center of the coordinate system, will be at the far left side of the beam. So in this case, it's at point A. Where does this line intersect the y-axis? It intersects at a positive 4. So that will be 4 kilonewtons per meter. The slope is negative because it's going down. And what is the value of that slope? Well, the height is 4 and the length is 6. So 4 over 6 reduces to 2 over 3. And the unit on slope is going to be units of force per length squared in this case. And we multiply that by x. So this is y equals mx plus b. It's a positive 4 with a slope of negative 2 over 3. After you have found the equation for this line, I strongly encourage you to go back and check it to make sure it's right. So if we plug in 0 for x to this equation, what do we get? We get a positive 4. That does indeed correspond with the line. There's a positive 4 right there. If we plug in 6 for this equation, so that would be at point B, what do we get? Well, 2/3 of 6 is 4, 4 minus 4 is 0, so that does indeed correlate with what we have in the diagram. You're required to write this down, the equation for this line, and I strongly encourage you to check it. Now I've drawn another free body diagram of the right-hand side of the beam. A couple of things to notice here. First of all, we have the distributed load redrawn here as a distributed load, not an outlined shape. We're not going to use a single point force here. We're instead going to use the equation for the distributed load. Notice everything to the left of this point has been removed. It's no longer acting on the beam. I always draw the beam with some thickness to help me remember that I actually cut the beam off. Remember, you are cutting the beam and the distributed load at that point. Also, I have drawn by on here. When you find a support reaction, you may accidentally assume a support reaction in the wrong direction. When you redraw that support reaction on the sectioned free body diagram, you must include its actual sense, so it is indeed going up. Now I need to apply my internal forces acting on this object. There are 3 of them, and they're all occurring over here at point C. The first one is my axial force. Remember that these forces must always be assumed in their positive sense. A positive axial force will stretch the section in question, so it's going to go towards the left. Now I'm going to draw my shear force. If you remember, the positive shear force causes clockwise rotation around the opposite side of the beam. So we're going to apply our shear force here at point C to produce clockwise rotation. That shear force would have to go up. Now we're going to draw the moment. A positive bending moment will compress the top fibers. So in this case, that's going to be clockwise. So there are my 3 internal forces, and now I can solve for those. And solving for internal forces is really nothing more than what we've already done in this course. And in order to solve for P, we would analyze forces in the x direction. By applying static equilibrium to the x direction on this section, we can solve for P. The thing to note here is that we can apply static equilibrium to parts of objects, not just the objects themselves. You can probably look at P and tell me that it's 0 kilonewtons without actually doing this, but these 2 steps are the minimum requirement to prove that it is. You must state your assumption of static equilibrium, and then you can say that P equals 0. That is not always the case. Make sure that you actually look at the object and apply static equilibrium correctly. To solve for V, then, we will apply static equilibrium in the y direction. The only unknown in the y direction is V. Now, I don't have L2 on the diagram, but L2 is the value of the force that replaces the distributed load. So then 0 equals Vy is simply V, it's positive. By is a positive By. And L2, the distributed load is going down, so that's going to be a negative value. And L is the force that replaces the distributed load. Remember, it's equivalent to the area. You have to look at the shape. This shape happens to be a triangle. The area of a triangle is 1/2 times base. In this case, the base is B, this length, times height. The height of the distributed load is the equation dl. That's y. Y equals 4 minus 2 over 3 times x. That's the height of this triangle. That'll tell you what this point is over here on the left side of the beam. Now remember, this is not 0, 0. 0, 0 is 3 meters further to the left at point A. This is just that we've sectioned the beam here. Now we can solve this equation for V, and now we can plug the numbers in. Now you might wonder, what do we plug in for x? X is the distance from 0, 0. If we're trying to figure out what y is, which is dl, x is the distance from the beginning of the origin. Remember that the origin is 3 meters towards the left. So that means that our x is actually going to be 3 meters, but it's not this 3 meters. It's the distance from point C, where we're trying to figure out what the height of this red line is. It's the distance from point C back to 0. So that's 3 meters. Now I realize this equation looks slightly more complicated than some of the equations we've done in the past. Remember that this is just static equilibrium. The difference here is that instead of having a single point force for this third term, it's the area of this shape. When you plug this all into a calculator, you will find that V equals a -1 kilonewton, which means V is actually going down. Don't worry about correcting the diagram. That's the answer. It's a negative. Don't try to include an arrow or anything on it. It's just a negative. To solve for Bm independently, we can sum moments at point C. If we sum moments at point C, the moment produced by P and the moment produced by V will be 0, and so the only unknown I'll be left with is Bm. I'm not writing the moments for P or V on here because they're going to be 0. So we've got the moment Bm, the moment produced by By, and the moment produced by the distributed load, which would be L2 times d perpendicular. In this case, my Bm is drawn as having a negative rotation. By is going to have a positive rotation, and its perpendicular distance is B. And the force that replaces the distributed load, if we hold this object at C, the distributed load is going to cause negative rotation. Now remember, the force that replaces the distributed load is equivalent to its area, so that's this equation over here. We've already figured out what L2 is. So that would be 1/2 times the base of the shape, which is B, times the height, which is DL. We also need to multiply that by the perpendicular distance. Since this is a triangle, the force that replaces it is going to be right about here, located at the centroid of the triangle. The centroid of the triangle is 1/3 of the base away from the side with the right angle. Right angle is right here, 1/3 away. That would be 1/3 of B, or B over 3, depending on how you wanted to write it. This is the force. This is its perpendicular distance. Solving this equation for BM gives this. And now we can plug the numbers in. Remember that X distance is 3 meters, but that's 3 meters away from the origin because we're analyzing this point right here. So we'll find that BM equals a positive 9 kilonewton meters. All three answers go in your answer box. The axial force is 0 kilonewtons, the shear force is -1 kilonewton, and the bending moment is positive 9 kilonewton meters. Why don't we use arrows? Why do we use just the signs? Well, if you included an arrow going down here on the shear force, that'd be extremely confusing because, yes, the shear force is going down in this part, but if that's the case, then it's going up on the left side of the diagram. So you would have to describe not only the arrow, but which side of the beam you were talking about, the left or right. Not only that, but that's going to change based on your orientation. If you look at the other side of the beam, it would be even more confusing to figure out which side you're talking about, which left are you talking about, which right are you talking about. So instead of trying to do that, we just give positive or negative signs with these answers.